Welcome back to The Explainer. Today, we're taking you from just being a passive breather to an absolute elite citizen scientist. We're going to merge some sleek, modern engineering with a little bit of that mad scientist laboratory energy to give you total control over your environment. We are talking about building your very own high-tech air quality monitor from scratch, processing raw telemetry, and literally hacking your own airspace. So get ready, because we are going full Dexter's Laboratory meets Silicon Valley Garage today.
Okay, let's just dive right into this invisible threat by asking the absolute most fundamental question every maker and citizen scientist needs to answer. What is actually in the air you're breathing right now? You know, we spend the vast majority of our lives indoors, totally oblivious to the unseen gases, smoke, and particulate matter just building up around us. But true hackers, we don't leave things to chance. We measure, we quantify, and we take control.
And listen, you really don't need a PhD or some massive government grant to pull this off. As the EPA points out, citizen scientists are using increasingly reliable, low-cost air pollution monitors to collect real environmental data. The power has completely shifted. With the right hardware, you can execute environmental monitoring that used to be strictly reserved for advanced institutions. We're going to build a device that tracks your air quality in real time.
Section 1. Build your own lab, the blueprint.
All right, let's look at our hardware payload. It's an incredibly accessible, super low-cost, yet highly capable stack. The brains of the whole operation is the ESP32 microcontroller. It's a tiny little powerhouse with built-in Wi-Fi. Hooked up to that, we've got our sensory organs, the MQ135 sensor, which we specifically chose to detect CO2, and the MQ2 sensor, our rapid response detector for LPG, smoke, and other combustible gases. Throw in a mini breadboard and a few jumper wires, and boom, you have the physical architecture of a highly sensitive environmental monitoring gadget.
The logic of our system code is just beautifully straightforward. Step 1. The ESP32 boots up and immediately connects to your local Wi-Fi network. Step 2. It reads the raw analog data coming from those MQ135 and MQ2 sensors. Step 3. It takes those raw values and computes a custom air quality index. And finally, Step 4. It fires all that processed data wirelessly right into the cloud using the ThingSpeak API. No bulky screens required here, just pure, continuous data streaming.
Now, any veteran of the hardware bench will tell you that true hackers anticipate obstacles. So here's a mission-critical troubleshooting step. These MQ sensors are not instantly plug-and-play. They actually require a calibration warm-up phase. You have to let them burn in for a few minutes to stabilize before you can trust any of the readings. Plus, the ESP32 can be notoriously finicky with power. A weak USB port is going to cause boot loops, for sure. You've got to give it a highly stable 5-volt power supply directly through the VIN pin to guarantee rock-solid reliability.
Section 2. The physics of sensors.
Okay, to really grasp advanced CO2 detection, we have to look under the hood at NDIR, or non-dispersive infrared sensors. This is where the magic actually happens. An NDIR sensor is basically a miniature optical chamber. It measures gas concentration not through some chemical reaction, but by reading the decrease in transmitted infrared light. And that decrease is perfectly proportional to the amount of target gas present. We are quite literally using light to count invisible gas molecules. How cool is that?
Picture this. Imagine a tube of air. We shine infrared light straight through it. The CO2 gas molecules inside that tube are going to absorb a very specific band of that IR light, while letting all the other wavelengths pass right on through. At the far end of the tube, an optical filter blocks absolutely everything except the specific light that CO2 interacts with. The detector then just measures what's missing. The more light missing, the more CO2 is in the room.
And get this, the exact specific wavelength of infrared light that CO2 molecules absorb, 4.26 microns. That is the magic number. By engineering an optical filter that isolates exactly 4.26 microns, the sensor completely ignores every other gas in the room and zeroes in entirely on the carbon dioxide. It is a brilliant piece of highly targeted physics just sitting right there on your desk.
Section 3. Testing your environment. The field test.
Before we can actually evaluate the air, we have to define the physical boundaries of our test environment. You need to measure your room's length, width, and ceiling height. Multiply those together and you get your functional volume in cubic feet. Basically, you're mapping out the exact spatial parameters that your new hardware is going to be monitoring.
Next up is a surprisingly low-tech but honestly brilliant diagnostic hack, the tissue test.
Because, hey, you don't always need microchips to understand fluid dynamics. By simply holding a regular tissue near a slightly ajar door, you can instantly determine your room's pressurization. If the tissue blows away from the door, your room is positively pressurized compared to the hallway. If it gets sucked toward the door, it's under negative pressure. It's just a remarkably quick way to visualize invisible airflow mechanics.
Now, for the ultimate test of your room's ventilation, the Harvard Guide recommends the CO2 decay test, and this is an incredibly badass process. You vacate the room, set up some mixing fans, and introduce dry ice, which, remember, is solid carbon dioxide. As it sublimates, it safely floods the room with CO2. Then you just step back and watch your ESP32 monitor track the decay rate. By measuring exactly how fast the CO2 levels drop, you can calculate precisely how quickly fresh outdoor air is replacing your indoor volume.
But we absolutely have to play it safe in the lab. When you're working with dry ice, there is a hard, non-negotiable limit you must respect: 5,000 parts per million. You must never let indoor CO2 exceed this occupational exposure limit during your decay tests. We want to measure the air, not weaponize it. Safety first, data second.
Section 4. Master your airspace.
So remember that custom algorithm running on our ESP32? Well, it takes the raw analog readings from our MQ sensors, normalizes them, and runs them through a weighted calculation, giving 70% priority to the CO2 sensor and 30% to the smoke and gas sensor. The code then classifies the final result into 5 specific air quality index categories, from excellent down through good, moderate, poor, all the way to hazardous. This right here is the real-time translation of complex chemistry into actionable human insight.
Finally, let's establish a real-time telemetry. Our system pushes this categorized data right up to the ThingSpeak Cloud API. But notice the timing here. It updates every 15 seconds. Why? Because a properly engineered system respects its constraints. Hitting the API too fast is going to trigger an Error 429 quota limit lockout. So a 15-second delay is the precise engineered sweet spot. It gives you a constant dynamic graph of your air quality while gracefully dodging the server's rate limits.
All right, you now possess the hardware blueprint, you understand the quantum physics of NDR optical sensors, and you know exactly how to execute professional-grade airflow testing protocols. You have absolutely everything you need to bring the invisible world to light. So, my final question to you is this: what invisible threats will you discover when you finally start hacking your own air? Grab a breadboard, fire up that soldering iron, and let's find out. Thanks for joining me on this explainer, and I will catch you on the next deep dive.